In today's class, we are going to take up an important concept in differentiation, and that is derivatives of implicit functions. So, viewers, we have already learned how to differentiate functions using chain rule and by making use of the elementary results in differentiation. Now, sometimes the functions are given not in the form of y is equal to fx, but in a more complicated form in which it is impossible to express y explicitly in terms of x, and such functions are called implicit functions, right? So here let us take an example. Suppose we have say y is equal to x square plus 2. Now this is a function of y is a function of x, and it can be written as y equal to x square plus 2, that is equal to f of x. Now here x is known as the independent variable and y is known as the dependent variable. Now here y can be expressed in terms of x. So this is an explicit function. So the definition of explicit function is, it is a function in which the dependent variable y is expressed in terms of some independent variable x. So here we have taken an example, and suppose we want to differentiate it. Then what we will do, we'll find we'll differentiate both sides with respect to x. So dy over dx is equal to the derivative of x square with respect to x plus the derivative of 2 is 0 because it is a constant, and we know that the derivative of a constant is 0. So this is equal to 2x. Now similarly, if we have a function say y is equal to square root of 2 minus x square, then here y is expressed explicitly in terms of x. So this form of the function is of the form y is equal to f of x. So here if we want to find the derivative, then differentiating both sides with respect to x, we have dy over dx is equal to the derivative of square root of 2 minus x square. Now this is equal to half multiplied by square root of 2 minus x square, 1 over 2 times square root of 2 minus x square, and then we have with the help of chain rule the derivative of 2 minus x square. So this is equal to 1 over 2, this is square root of 2 minus x square, and the derivative of 2 minus x square is this is the derivative of 2 is 0. So here we have 0 minus 2x. So this is minus x divided by square root of 2 minus x square. So viewers, this is how we find the derivatives of explicit functions. So what are explicit functions? So it is a function in which the dependent variable y is expressed in terms of some independent variable x. So here I have quoted 2 examples. Now let us take some examples of implicit functions. So let me remind you once again, the definition of implicit function: it is a function in which the dependent variable y is not expressed in terms of some independent variable x. So let us take an example. So suppose we have an expression like this: x square plus y cube minus 2x plus 6y minus 10 is equal to 0. Now if we look at this expression, then we can easily see that y cannot be expressed as y equal to f of x. So such expressions are known as implicit expressions, right? And such functions are known as implicit functions. Now here it would be quite difficult to rearrange to get the form y equal to fx. So such a function given in this way is said to be defined as implicitly. Now in order to find out the derivative of such expressions, what we do, we will differentiate both sides with respect to x. So differentiating both sides with respect to x, right? Okay, now here we will do the differentiation term by term. So here the derivative of x square is 2x. So let us first write it in this way. So we have d by dx of this is y cube. Then we have the derivative of minus 2x, and then we have derivative of 6y, and the derivative of 10 is 0, right? Now the derivative of x square is 2x. The derivative of y cube is 3y square, and then we will have here dy over dx due to chain rule, right? Because here we are differentiating with respect to x, but when we differentiate y cube with respect to y, then we get 3y square and an additional term, that is dy over dx. And here the derivative of x is 1, so we have here simply minus 2, and then here we have 6, and this is dy over dx, and this is equal to 0, right? So here the derivative of 10 is 0 because it is a constant. Now once we have obtained this expression, now we'll collect the terms containing dy over dx. So collecting the terms, we have here 2x minus 2, then we have 3y square plus 6, and here we have dy over dx equal to 0. Now taking this term to this side, we have 3y square plus 6 dy over dx equal to this can be written as 2 minus 2x, and then dy over dx is equal to 2 minus 2x divided by 3y square plus 6, right? So this is the derivative of y with respect to x. So viewers, the process of differentiating an implicit function is known as implicit differentiation, and by implicit differentiation we get the derivative of y with respect to x. Now let us take one more example. So here we have to find dy by dx if x square times y plus y square equal to x cube is given. So again this is an example of implicit differentiation. Here we have to find the derivative of y with respect to x, and this is an implicit function. So what we will do, we'll differentiate both sides with respect to x. So let us differentiate both sides with respect to x. So here we have d by dx of x square y plus y square equal to d by dx of x cube, right? Now here we have the derivative of x square times y plus derivative of y square, and then we have here we'll apply this rule, that is the derivative of x raised to n is nx n minus 1, so here we have 3x square. Now viewers, here we would apply the product rule for finding out the derivative of the product of two functions. Here u and v are the two functions of x, so we'll apply this rule. So here we can write it as x square times the derivative of y, then we have y, and derivative of x square, that is 2x, and this is the derivative of y square with respect to x is 2y dy over dx, and this is equal to 3x square. Now again, what we will do, we will collect the terms containing the derivative of y with respect to x. So we have here x square plus 2y, and here we have dy over dx, and taking this term to this side, we have 3x square minus 2xy. So this can be written as dy over dx, that is equal to 3x square minus 2xy divided by x square plus 2y. So this is the required derivative dy over dx. Now let us solve one more problem. So here we have to find dy over dx when the expression sin y plus x square plus 4y equal to cos x is given. So again, here we'll make use of the implicit differentiation process, and this is an implicit function. So let us differentiate both sides with respect to x. So we have here d by dx of sin y, then we have the derivative of x square, and then we have the derivative of y, and in the right hand side we have the derivative of cos x. So now the derivative of sin y, and here we have to differentiate it with respect to x. So first we will differentiate sin y with respect to y. So we have cos y, and then by chain rule we have dy over dx, and here we will apply this rule. So the derivative of x square is 2x plus this is 4 times dy over dx, and the derivative of cosine function is minus sine function, right? Again we will collect the term containing the derivative of y with respect to x. So we have cos y plus 4, and this is dy over dx, and taking this 2x to the right hand side, we have minus 2x minus sine x. So this can further be written as dy over dx that is minus of 2x plus sin x divided by cos y plus 4. So this is the required expression for dy over dx. Now let us consider one more problem. Here we have to find dy over dx for this expression that is xy plus y square equal to tan x plus y. So again we'll differentiate both sides with respect to x. So what we will get, we have the derivative of the product of x and y. Here we have the derivative of y square, then we have the derivative of tan x, and this is dy over dx, right? Okay, now here we have the product of x and y, so we will apply this rule here. So this is x, then derivative of y, then plus y, and derivative of x is 1, and the derivative of y square is 2y dy over dx, and the derivative of tan x is sec square x, and here we have dy over dx. Now viewers, again what we will do, we will collect the terms containing dy over dx. So here we have x, then we have plus 2y, and if we take dy over dx to this side, we have minus 1, and this is dy over dx, and taking this y to this side, we have sec square x minus y. So dy over dx is equal to sec square x minus y divided by x plus 2y minus 1. So this is the required expression for dy over dx. Now let us take one more important problem. Here we have to find dy over dx, and the expression is given as x square plus xy plus y square equal to pi. Now again the same process will follow, that is, we'll differentiate both sides with respect to x. So here we have the derivative of x square, then we have d by dx of xy, and then we have d by dx of y square, and the derivative of pi is 0, because pi is a constant here, and we know that the derivative of a constant is 0. Now the derivative of x square is 2x, and here we will apply the product rule. So this is x dy over dx, then we have y, and the derivative of x is 1, and the derivative of y square is 2y dy over dx, and it is equal to 0. So again, collecting the terms, we have 2x plus y, and here we have x plus 2y dy over dx. Now x plus 2y dy over dx is equal to, taking this term to the right hand side, so we have minus 2x plus y. So the final expression for dy by dx is equal to minus we have 2x plus y divided by x plus 2y, right?